Picture the universe 1 second after the Big Bang. Not a metaphor, not a classroom diagram. The real thing. A fireball so hot that matter and antimatter were constantly forming and destroying each other, billions upon billions of times per second, in every direction, in every corner of existence. Physics says that explosion should have made equal amounts of both. For every proton created, one antiproton. For every particle of matter, one mirror particle of antimatter. And when they touched, both would vanish in a burst of pure light. Equal partners, equal destruction. The math adds up perfectly. The universe should have ended before it ever began, with nothing left but a dying glow stretched thin across an empty void. But instead, here you are. You exist. The Earth exists. Every star you have ever seen in the night sky exists. Every ocean, every mountain, every city, every bone inside your body. All of it is matter that should not have survived. And the question that has haunted physics for more than 50 years is this one: why? Why did matter survive and antimatter did not? Why is there something instead of nothing? In July of 2025, a team of scientists at the most famous physics laboratory on Earth achieved something that had never been done before. They caught a single particle of antimatter and held its inner compass spinning in perfect rhythm for 50 seconds. Not a collection of particles, not a simulation, not a shortcut, one antiproton, alone, controlled, oscillating like a clock built from the universe's oldest secret. The baryon-antibaryon symmetry experiment, known as BASE, sits inside the antimatter factory at CERN in Geneva, Switzerland. CERN is the European Organization for Nuclear Research, a scientific collaboration founded in 1954 by 12 nations. Today, it has 23 member states, and its underground complex on the border of France and Switzerland is home to the most powerful particle physics laboratory in the world. The Large Hadron Collider, buried 40 meters beneath its campus, is 27 kilometers in circumference. The antimatter factory, located in a separate hall above ground, is the only place on the planet where antiprotons are routinely created, slowed down, and studied with precision. 2 successive deceleration rings, the antiproton decelerator and the extra-low energy antiproton ring, known as ALINA, take the antiprotons produced by smashing high-energy protons into a metal target and slow them down from nearly the speed of light to speeds that can be captured in electromagnetic traps. The antiproton decelerator delivers approximately 400 million antiprotons per hour to the experiments it serves. Of those, the experiments capture about 10%. The BASE collaboration itself was established in 2013. It includes scientists from Germany, Japan, the United Kingdom, Switzerland, and several other countries, including institutions such as Heinrich Heine University in Düsseldorf, the Max Planck Institute for Nuclear Physics in Heidelberg, Riken in Japan, and GSI and FAIR in Darmstadt. Their goal is precise and singular, to compare the properties of a proton and an antiproton so carefully that if the two particles differ by even 1 part in a trillion, they will catch it. Because that difference, however tiny, might be the answer to why anything exists at all. If you value documented physics history like this, subscribe. It is the best way to support our work. Also, tell us in the comments what city you are hearing this from right now. The script is researched and factual, using sources including the BASE experiment's own published paper in Nature, volume 644, pages 64 through 68, 2025, with lead author Barbara Maria Latas, and co-authors including Stefan Ulmer, Christian Smora, and Klaus Blaum, a paper selected as one of the top 10 physics breakthroughs of the year by Physics World magazine. Sources also include official press releases from CERN and the BASE collaboration's own website at base.web.cern.th. Now back to the story. To understand what BASE actually did in 2025, you need to understand what a proton is, at the deepest level anyone has ever looked. A proton is not just a tiny ball, it has a property called spin. Spin in quantum physics is not quite like the spin of a top, but the best way to picture it is to imagine a compass needle. That needle can point north, which scientists call spin up, or it can point south, which is spin down. Those are the only 2 options. It cannot point sideways or diagonally or in any other direction. This spin creates a tiny magnetic force, and the exact strength of that force is called the magnetic moment. The magnetic moment tells you how strongly the particle responds to a magnetic field, how much the compass needle resists being turned, how much energy it takes to flip it from pointing one way to pointing the other. Now, an antiproton, the antimatter twin of the proton, has the same mass, but its electric charge is opposite. Where the proton has a positive charge, the antiproton has a negative charge. The antiproton also has a spin, also pointing up or down, and also a magnetic moment. According to the deepest and most well-tested rules of physics, a set of symmetry laws called CPT symmetry, The magnetic moment of the proton and the magnetic moment of the antiproton should be exactly equal in size, just pointed in opposite directions. CPT stands for charge, parity, and time reversal. It is not a guess. It is not an assumption. It is one of the most fundamental pillars of the Standard Model, the master theory that describes every known particle and every known force except gravity. According to theorems proven in the 1950s, any quantum field theory that is consistent with special relativity and has a stable vacuum state must obey CPT symmetry. If CPT symmetry holds, then a proton and antiproton are perfect mirror images of each other. If it does not hold, if their magnetic moments differ even slightly, then the entire framework of modern physics is incomplete, and that crack in the mirror might explain why the Big Bang produced more matter than antimatter. That is the experiment. Not looking for a big, dramatic difference, looking for something almost impossibly small, a deviation measured in parts per billion or parts per trillion. The challenge is not conceptual. The challenge is making a measurement that precise without the noise of the world drowning out the signal. The two particles behave like miniature bar magnets. To measure the magnetic moment precisely, scientists need to measure two frequencies. The first is called the Larmor frequency, the natural rate at which the spin precesses or wobbles inside a magnetic field. Think of it as the tick rate of the compass needle in the magnetic environment of the trap. The second is called the cyclotron frequency, the rate at which the charged particle circles around the axis of the magnetic field. The ratio of those two frequencies gives you the magnetic moment. To get a precise value of that ratio, you need to measure both frequencies with great accuracy, and the accuracy of both measurements depends on one thing above all others: how long you can observe the particle without the quantum state being disturbed. Every particle in the quantum world is fragile the moment it starts to interact with its surroundings, with stray magnetic fields, with vibrations in the floor, with the electromagnetic noise produced by nearby machines, with any form of thermal energy in the walls of its container. It loses its quantum behavior. This loss is called decoherence. Think of it like a tuning fork. If you strike a tuning fork and it rings at exactly 440 vibrations per second, you can measure that frequency with great precision if you let it ring for a long time. But if someone grabs the fork with their hand 1 second after you strike it, the ringing stops. The measurement fails. In quantum physics, almost everything is the hand grabbing the fork. Heat is a hand. A nearby wire carrying current is a hand. A tiny ripple in the background magnetic field is a hand. A vibration in the floor is a hand. Anything that touches the quantum state of a particle collapses it, destroys the measurement, and forces the scientist to start over. Before 2025, BASE had already achieved something remarkable. In 2017, they measured the magnetic moment of an antiproton to within 1.5 parts per billion precision. That was a world record, the most precise measurement of any property of any antimatter particle ever recorded. They published that result and earned international recognition. But that measurement was made using what scientists call an incoherent technique. In incoherent spectroscopy, you flip the spin with an electromagnetic pulse, then pull the particle over to the analysis trap and detect whether the spin went up or down. You do it again and again, hundreds of times, and you build a statistical picture of how likely the spin is to flip at different frequencies. It works, but it is blurry. The noise of the environment bleeds into the result. Each individual measurement is contaminated by the magnetic field fluctuations in the building. You average over many measurements, and the noise partially cancels, but only partially. You can push your precision only so far before the magnetic field fluctuations, 1/billionth of a Tesla, 20,000 times smaller than the magnetic field of the Earth, set a ceiling you cannot break through. The precision required to detect the subtle difference that might explain the matter-antimatter asymmetry of the universe sits below that ceiling. To get there, BASE needed a completely different approach. Coherent spectroscopy is that approach. In coherent spectroscopy, you do not just flip the spin and walk away. You keep pushing in perfect rhythm, like a parent pushing a child on a swing at exactly the right moment every single time. With each perfectly timed push, the swing goes higher in a smooth, predictable arc. The spin is not flipping randomly. It is oscillating in a controlled wave, called a Rabi oscillation, named for physicist Isidore Rabi, who won the Nobel Prize in Physics in 1944 for discovering how to probe the magnetic properties of atomic nuclei using radio frequency resonance. A Rabi oscillation is a smooth back and forth between spin up and spin down, driven by a resonant electromagnetic pulse and evolving in a mathematically precise pattern. The longer the oscillation runs cleanly, the more precisely you can measure the frequency driving it. And that frequency is the Larmor frequency, one of the two numbers you need for the magnetic moment calculation. This is not a technique invented for antiprotons. Coherent spectroscopy has been used for decades in large collections of particles. Scientists measure proton and deuteron magnetic moments this way, using hydrogen macers, devices that exploit the coherent oscillation of many billions of hydrogen atoms simultaneously to reach parts per trillion precision. Mass spectroscopy with protons has reached subparts per trillion resolution. But all of those experiments work with enormous clouds of particles at once. The noise of one particle is averaged out by the signal of billions of others. Doing coherent spectroscopy on a single particle, one lone antiproton, isolated from everything else, with no crowd to average out the fluctuations, is categorically different. The signal is one particle's spin. The noise is the entire world pressing in on it. According to the BASE team, coherent quantum transitions had been observed before in large collections of particles and in trapped ions. But for a single free nuclear magnetic moment, one isolated nucleus-like particle, it had never been done. Physics textbooks described it as a goal. Decades passed. No laboratory achieved it, not with ordinary matter, and never until 2025 with antimatter. The experimental setup inside BASE is a stack of electromagnetic containers called penning traps. A penning trap uses a combination of static electric fields and a strong magnetic field to hold a charged particle in place without letting it touch anything. The particle floats, suspended in fields, going nowhere, touching nothing, surrounded by a vacuum better than what exists in outer space. The BASE trap stack that achieved the 50-second result has 5 distinct zones arranged in sequence. The reservoir trap holds a bank of up to 100 antiprotons at a time, waiting in storage. The parking trap holds a single antiproton between measurement cycles. The shielded precision trap, surrounded by a new superconducting metal structure designed to cancel external magnetic noise, is the room where the spin oscillation happens. The analysis trap uses the continuous Stern-Gerlach effect, the application of a weak magnetic bottle superimposed on the trap to detect which direction the spin is pointing after each measurement. And the cooling trap brings the particle's energy down to below 200 millikelvin. That is 0.2 degree above absolute zero, the coldest temperature the laws of thermodynamics allow anything to reach. The Stern-Gerlach principle behind the analysis trap has a history going back to 1922. In that year, German physicists Otto Stern and Walther Gerlach sent a beam of silver atoms through an inhomogeneous magnetic field and observed that the beam split into 2 distinct bands on the detector plate behind it. Not a smear, not a gradient, but 2 clean lines. This proved that the magnetic spin of an atom can only take discrete values, not a continuous range. It was one of the first direct experimental demonstrations of quantum mechanics at work. A century later, BASE uses a modern adaptation of this principle. When the antiproton's spin is pointing up, its axial oscillation frequency in the trap is very slightly different than when the spin is pointing down. The difference in frequency is a fraction of a hertz, almost unmeasurably small in any other context. But inside the cryogenic trap, with the particle cooled to below 200 millikelvin, that tiny frequency difference becomes readable. Spin up or spin down, a clear signal, no guessing. Here is the thing that makes the 50-second result so difficult to appreciate without the right context. The CERN facility that houses BASE is, by the standards of precision physics, an extremely noisy environment. Not acoustically noisy. The noise is electromagnetic and magnetic. The antiproton decelerator that feeds antiprotons into BASE operates at high currents and generates magnetic field fluctuations throughout the surrounding building. The power lines, the cooling systems, the motors and pumps needed to run the accelerator complex. All of them produce tiny oscillations in the local magnetic field. Those fluctuations are on the order of 1/billionth of a Tesla. To put that in perspective, the magnetic field of the Earth at its surface is approximately 50 millionths of a Tesla. The fluctuations inside the BASE building are roughly 20,000 times smaller than the Earth's field, so small that no instrument outside the building would detect them. Completely invisible to any measurement not as sensitive as BASE itself. But BASE is that sensitive. And those fluctuations were enough before the 2025 upgrade to knock a quantum state sideways in well under a second. The spin oscillation that needed to run for 50 seconds to build high-precision measurements was simply impossible in that environment. The breakthrough came through 2 simultaneous engineering advances. First, the team built a new superconducting shielding structure around their precision trap. Superconductors are materials that, when cooled below a critical temperature, carry electrical current with 0 resistance. This property makes them ideal for creating perfect static magnetic fields with no drift and for canceling incoming magnetic noise. The new shielding structure is itself a penning trap component, made of superconducting metal and shaped to redirect and cancel the fluctuations coming through the walls of the laboratory. It does not eliminate the noise at the source. The accelerator keeps running, the magnets keep cycling, but it stops the noise from reaching the antiproton inside the precision trap. Second, the team improved the cyclotron cooling technique. Published in a Physical Review Letters paper in 2024, also authored by Barbara Maria Latas and colleagues, the new cooling method chilled the cyclotron mode of a single-trapped antiproton to below 200 millikelvin in under 500 seconds. Cyclotron mode cooling means reducing the energy of the particle's circular orbit around the trap axis, slowing its circular motion until it is almost perfectly still. A colder particle is a quieter particle. A quieter particle holds its quantum state longer. Both improvements together, the shielded precision trap and the subthermal cyclotron cooling, allowed the team to attempt something never done before. A single antiproton pulled from the reservoir trap and moved through the parking trap into the shielded precision trap, cooled to below 200 millikelvin. Electromagnetic pulses applied at the Larmor frequency, the resonant frequency of the antiproton's spin in the magnetic field of the trap, timed with precision down to fractions of a microsecond. Each pulse a push on the swing, spin up to spin down to spin up. The oscillation began. It ran. 10 seconds, 20 seconds, 30 seconds, 40 seconds, 50 seconds of coherent Rabi oscillation in a single antiproton spin. The curve of the oscillation, measured and plotted against time, showed the smooth sinusoidal shape that coherent quantum mechanics predicts. Not noise, not randomness. A real wave, generated by one lone particle of antimatter held still in an electromagnetic cage at 200 millikelvin in a laboratory in Geneva. Stefan Ulmer, founder and spokesperson of BASE and professor at Heinrich Heine University Düsseldorf, described the result directly. "This is the first antimatter qubit," he said, "and it opens the prospect of applying the entire set of coherent spectroscopy methods to single matter and antimatter systems in precision experiments. Most importantly," he said, "it will help BASE perform antiproton moment measurements with 10 to 100 times improved precision in future experiments." Barbara Latas, the lead author and a research scientist at CERN, explained that the achievement sets the stage for future measurements at a quieter facility where coherence times could perhaps stretch to 500 seconds, 10 times longer than the 50 already achieved. Subscribe if you want more documented science history like this. Comment your city below. Back to the story. The 50 seconds is not just a record for the sake of records. It is precision, and precision in this context is the difference between being able to see a signal and not being able to see it at all. In frequency measurements, and measuring a magnetic moment is fundamentally a frequency measurement. The longer your signal runs cleanly, the narrower the range of frequencies you can resolve. It is the same principle that makes a very long musical note easier to tune precisely than a very short one. A note held for 50 seconds gives you a frequency resolution roughly 50 times finer than a note held for 1 second. For the antiproton magnetic moment, that translates directly into measurement precision. The current best measurement of the antiproton magnetic moment sits at 1.5 parts per billion. Multiply the precision by 100, the upper end of what coherent spectroscopy can offer, and you reach 15 parts per trillion. At that resolution, a violation of CPT symmetry 100 times smaller than any previously detectable difference would become visible. Any violation of CPT symmetry at any scale is physics beyond the standard model. Physics that might tell us why the universe chose matter over antimatter. Why is there more matter? The current answer from the standard model is that it did not produce more matter, not enough to explain what we observe. Physicists calculated in the 1960s and 70s that the amount of CP violation already known in particle physics, the asymmetry in how certain mesons decay, observed in experiments at Brookhaven National Laboratory and later at particle colliders worldwide, is roughly 9 orders of magnitude too small to explain the observed ratio of matter to antimatter in the universe. 9 orders of magnitude means 1 billion times too small. The excess of matter we see cannot be explained by the physics we have found so far. Something else happened in the first moments after the Big Bang. Some additional mechanism broke the symmetry further than any known process can break it. The name physicists give to the conditions needed for this to happen is the Sakharov conditions, after Soviet physicist Andrei Sakharov, who laid them out in 1967. One of those conditions is violation of CP symmetry beyond what the standard model predicts. The hunt for that additional violation has driven particle physics experiments for more than 5 decades. In March of 2025, at the annual Rencontres de Morion conference in La Tuile, Italy, the LHCb collaboration at CERN announced a separate result, the first ever observation of CP violation in baryon decays, meaning the first time matter-antimatter asymmetry had been seen in the decay of protons and neutrons and their relatives. Published in Nature in July of 2025, that result used more than 80,000 baryon decay events collected by the Large Hadron Collider. It was the 4th subatomic particle system known to show CP violation. It confirmed that the asymmetry exists in the baryon family. the family that includes protons and antiprotons, not just in the meson family where it had been known for decades. But the amount of CP violation measured there is still far too small to explain the universe. The door is open, but the room behind it has not yet been found. That is why base matters. The two experiments, LHCb measuring CP violation and decays, base measuring the magnetic moment of a single antiproton, are approaching the same question from different directions. LHCb counts billions of particle decays and looks for statistical asymmetries. Base freezes one particle to 0.2 of a degree above absolute zero and listens to its spin for 50 seconds. Both are searching for the fingerprint of whatever broke the universe's symmetry at the beginning. Neither has found it yet. Both are getting closer. The limitation of base at CERN is the building itself. The magnetic noise floor set by the antiproton decelerator and all of its equipment has now been pushed as far down as possible inside that facility. The shielded precision trap and the subthermal cooling have brought the coherence time to 50 seconds. Going meaningfully beyond that, to 100 seconds, to 500 seconds, requires removing the antiproton from the source of the noise. That is the purpose of base step. Base step, symmetry tests and experiments with portable antiprotons, is an apparatus designed to trap antiprotons at CERN's antimatter factory and carry them to quieter locations. The device weighs approximately 1,000 kilograms. 600 kilograms of that is the superconducting magnet, which must be kept below 8.2 Kelvin, negative 264.8 degrees Celsius, at all times for the superconductivity to hold and the magnetic trap to remain functional. The device is small enough to pass through ordinary laboratory doors. It sits on a truck. It contains its own power reserves and its own cryogenic cooling. In October of 2024, the team transported a cloud of 70 ordinary protons, not antiprotons, across the CERN campus as a dress rehearsal. That test, the first time any loose particles had ever been moved in a reusable portable trap, confirmed the basic engineering worked. On March 23, 2026, they did it with real antimatter. 92 antiprotons trapped inside the cryogenic penning trap of base step were disconnected from the main experimental facility, loaded by crane onto a truck, and driven across CERN's main site. The journey took several hours. At no point did the superconducting magnet warm above its critical temperature. At no point did the trapped antiprotons escape their cage. When the truck stopped and the system was checked, the antiprotons were still there. A bottle of champagne was opened. CERN's Director for Research and Computing, Gauthier Hamel de Moncheneau, said publicly that transporting antimatter is a pioneering and ambitious project, and that the result marks the beginning of an exciting scientific journey that will allow the physics community to further deepen its understanding of antimatter. The energy released if all 92 antiprotons in base step annihilated at once would be approximately 1/1,000,000th of a joule, less than the energy stored in a single raindrop falling a few centimeters. The danger is not the energy. The danger is the loss of the experiment itself. Months of work to retrap and prepare the particles, gone in a flash of gamma rays and pions. The truck ride across campus was a first step. The real destination is 8 hours away. Heinrich Heine University Düsseldorf, where a dedicated offline laboratory is being built to receive the antiprotons and perform precision measurements in an electromagnetic environment free of accelerator noise. The plan also extends to Leibniz University Hanover and potentially other European laboratories. An antiproton delivery service, a phrase that would have sounded like science fiction 10 years ago, is now a matter of engineering refinement. Barbara Letach said it directly. A fully operational offline precision penning trap system at HHU, supplied with antiprotons from base step, could allow spin coherence times perhaps 10 times longer than current experiments. A game changer for baryonic antimatter research. The base experiment has been setting records since its founding. In 2015, they published in Nature the most precise comparison of the charge-to-mass ratio of the proton and the antiproton, 69 parts per 1,000 billion, confirming the Standard Model's prediction to that level. In 2017, they published the magnetic moment measurement at 1.5 parts per billion. In 2020, they stored a single antiproton for more than a year in their reservoir trap, the longest any antiproton has ever been kept alive in a laboratory. The best vacuum ever achieved in any experiment on Earth, 5 times 10 to the negative 19th millibar, was produced inside the base vacuum system, a pressure so low that a cubic meter of that space would contain fewer gas molecules than a cubic centimeter of the best vacuum achievable by conventional pumps at room temperature. The base experiment is not a series of one-time demonstrations. It is a program of steadily improving precision, each generation of results serving as the floor for the next. The 2025 coherent spectroscopy result is not the end of that program. It is a transition point, the incoherent era in which measurements were made one statistical flip at a time, noise-limiting precision, the magnetic environment of the building setting the ceiling, is over. The coherent era, in which a single antiproton spin is driven in a clean, controlled wave for 50 seconds, then one day for 500, carrying in its frequency the answer to a question older than any human institution, has begun. 1 billion years before CERN was built, 1 billion years before the first human looked at the night sky and wondered what the stars were made of. The matter that makes up those stars and the planets and the people looking up at them was created in the first second of the universe's existence and should have been destroyed in the second second. Something stopped that destruction. Some difference, too small to see with any instrument built so far, intervened. The 50-second oscillation of a single antiproton in a superconducting trap in Geneva is the most careful listening anyone has ever done for the sound of that difference. The truck stopped. The antimatter survived the road. The next trap is already waiting in Düsseldorf. The answer is still in the spin. There's a detail about antiprotons that most people do not know, and it matters for understanding why this measurement is so difficult. Antiprotons are not exotic or unstable. They do not decay. A proton will live for at least 10 to the 34th years. A number so large it makes the current age of the universe look like a blink. An antiproton, left in perfect isolation, will live just as long. It is not fragile in the way a radioactive nucleus is fragile. It is only fragile in one specific sense. It will annihilate instantly if it touches any particle of ordinary matter. Any contact at all. The wall of the trap is made of matter. The residual gas molecules and even the best vacuum are made of matter. The electrical leads connecting the trap electronics are made of matter. To keep an antiproton alive for a year, as BASE managed in 2020, requires achieving a vacuum so close to perfect that the antiproton almost never encounters a stray gas molecule, and keeping the electromagnetic fields stable enough that the particle never drifts to the wall. The vacuum inside BASE's trap has been measured at 5 times 10 to the negative 19th millibar. Earth's atmosphere at sea level is roughly 1,000 millibar. The interior of the International Space Station is also roughly 1,000 millibar. It is pressurized to be comfortable for astronauts. The vacuum of outer space between stars in our galaxy averages around 10 to the negative 17 millibar. The vacuum inside the BASE trap is approximately 100 times better than the average interstellar vacuum. That is not a misprint. The trap is emptier than most of space. That extreme vacuum is what makes antiproton storage possible. It is also what makes the measurement environment challenging in a different way. With so few gas molecules, there is nothing to damp vibrations mechanically, and any electromagnetic disturbance passes through without resistance. The fact that the BASE experiment sits at the only place in the world where antiprotons are produced adds a layer of constraint that most physics experiments do not face. You cannot build a quieter lab for antimatter research and then ship antiprotons to it, because antiprotons annihilate the moment they touch any ordinary matter container that is not electromagnetically sealed. The antiproton decelerator at CERN is that seal. It produces the low-energy antiprotons that experiments need. Moving away from it, even across CERN's own campus, even to Düsseldorf 8 hours away, requires a self-contained, electromagnetically shielded, cryogenically cooled, mechanically robust transport trap that has never existed before in the history of physics. BASE STEP is that trap. It was described in detail in a paper published in the Review of Scientific Instruments in November of 2023, authored by Smora and colleagues, giving the full technical design of the system before the first transport tests were run. The physics at stake in these measurements is not abstract. It connects directly to the question of what you are made of and why you are here at all rather than not. The Standard Model, for all its success in predicting the behavior of particles in accelerator experiments, gives a spectacularly wrong answer when asked about the universe as a whole. It predicts that the Big Bang should have made equal amounts of matter and antimatter. Observations confirm that the universe today is made almost entirely of matter. The discrepancy between the prediction and the observation is not a small rounding error. The observed excess of matter over antimatter is 1 part in approximately 1 billion, about 1 matter particle surviving for every billion matter-antimatter pairs that annihilated. Whatever produced that 1 in a billion survival rate is not described by any equation currently in any physics textbook. It is new physics. It is undiscovered physics. And one of the most plausible places to look for its fingerprint is in the precise comparison of proton and antiproton magnetic moments. Every measurement BASE makes of the antiproton's magnetic moment is also a measurement of what is not there. If the proton and antiproton magnetic moments are exactly equal, that confirms CPT symmetry holds to the level of precision achieved. It does not prove new physics exists, but it does push the limit lower. Any new interaction that couples differently to matter and antimatter, a new boson, a new field, something not yet in the Standard Model, would show up as a tiny difference in the magnetic moments. The sensitivity of the measurement determines how faint that signal can be and still be detectable. Before 2017, The sensitivity was 1 part per million. After 2017, it was 1.5 parts per billion, 600 times more sensitive. After the coherent spectroscopy program reaches its full potential at Heinrich Heine University Düsseldorf, it could be 100 to 1,000 times more sensitive still. If the signal is there, those measurements will find it. The word qubit appeared in the headlines after the Nature paper was published in July of 2025. Antimatter qubit, first antimatter qubit, quantum bit in an antiproton. The language of quantum computing attached itself immediately to the result. Journalists and science communicators correctly identified the parallel. A qubit is a quantum two-state system used to store and process information. An antiproton with a spin that can be prepared in spin up, spin down, or any superposition of the two, a state that can be coherently controlled for 50 seconds, is, by the mathematical definition, a qubit. But the base team and base spokesperson Stefan Ulmer were careful to separate the result from any suggestion of an antimatter quantum computer. The practical barriers are enormous. Antiprotons are produced at one facility on Earth. The cost of producing and storing a single antiproton is immense in terms of accelerator time and infrastructure. The fragility of the system, one stray molecule, one magnet quench, one power failure, would destroy the stored particles instantly. Quantum computers made of antiprotons are not on any roadmap. The significance of the first antimatter qubit is not computational, it is spectroscopic. The same techniques that quantum computing uses to control qubits, coherent pulses, Rabi oscillations, controlled state preparation, can now be applied to a single antiproton for precision measurement. That is the game changer. In the months following the 50-second result, the Physics World editorial board evaluated hundreds of physics papers from 2025 and selected the base coherent spectroscopy paper as one of the top 10 breakthroughs of the year. The selection was based not just on technical novelty, but on scientific impact. What the result opens up, what becomes possible that was not possible before. The paper demonstrated for the first time that a single free nuclear magnetic moment can be held in coherent superposition. Not an ion. An ion is a charged atom, which has electrons surrounding a nucleus, and the electron's spin can partially shield the nuclear spin from external noise. An antiproton is a bare nucleus with no electron shield. It interacts with the magnetic field directly and completely. Achieving coherent spectroscopy under those conditions is harder than in trapped ions, and yet BASE achieved it, not in the quietest laboratory in the world, but in the noisiest room any precision physicist has to work in, the antimatter factory at CERN, next to a high-current particle accelerator running around the clock. The final move, taking BASE step across the CERN campus on March 23, 2026, was the experimental proof of a concept that the entire next decade of BASE's research depends on. If the trap had failed, if the superconducting magnet had quenched during the journey, if vibration from the road had sent the antiprotons spiraling into the trap walls, the program would have faced a major setback. It did not fail. The 92 antiprotons completed their journey. The cryogenic system held its temperature. The experiment continued operating after the truck stopped and the system was reconnected. Christian Smora, the head of the BASE step team, said the validation with protons in 2024 was important. But he called what they achieved with antiprotons in 2026 a huge leap forward toward the objective. The destination, 8 hours away, down the Autobahn from Geneva to Düsseldorf, through the Rhine Valley, past cities built on ground that has nothing to do with particle physics, is now within reach.